And I'm killing time hoping that Paul Gabor can show up. I hadn't heard that he wouldn't be here.
Can't you just knock on his wall, or is he
Well,
up to that?
he's at the house next door, so I'd have to leave the room. I can knock on the wall for
Rob
Rob.
Lorenz, but no, Rob Lorenz is in the office.
Right. And Larry's having internet problems. All right.
Oh gosh.
Well, we'll live without him for the moment. All right, well, we may as well get going. Welcome, everybody, to the first full moon meetup of the year. And as is our wont, we'll do a little bit around of tell us what you've seen over the last month, where you are, and what's the weather. So we'll start with you, Jeff. And you're muted.
Okay. Is it okay now?
Yep.
Hey, yeah, it's 40 degrees and cloudy here in Manaville, New York. I haven't seen anything over the month, but the weather's been better the last couple of days. It was like an icebox here a couple of days ago, so really cold. But unfortunately, I haven't seen anything unusual in the sky.
Okay. Joel.
Yes, here in Green Valley, we've endured several freezes, quite unusual. And it's about in the mid-30s right now, still rather chilly. I did have the wonderful opportunity to share some viewing with Fathers Paul and Chris last weekend, and we looked at Orion's Nebula, the Horsehead Nebula, and had a wonderful evening.
Linda.
Well, it's been cold here, and I did see some planets, and I saw the moon, but then it was very cloudy. So we weren't able to really see too much.
And remind people you're in Allentown, right?
Allentown, yeah.
Okay, Marianne.
I'm in Luxembourg. We have a gorgeous winter day today. Blue sky, sun, really cold, frozen lakes. And I think the comet that one can see tonight is Tsushishan Atlas.
Okay, and Bob, you'll try to put a note to that in the chat.
Yes, I will.
Joe.
Hello, good morning from Phoenix. I'm in the middle of the city, so it's hard to see anything but Jupiter and Venus. I did see Venus and the moon very close, but also, unfortunately, some drones.
Yep. Okay. Dennis.
I am in Denver, Colorado. We're having winter weather, clear skies, highs in the 30s, lows in the teens. In the city, so can't see much in the sky at night, but I got a great view of the moon late afternoon from Tabletop Mountain in a ranch where my daughter was taking a riding lesson.
Oh, lovely. Rob.
Yep, I'm here in sunny Tucson, and yeah, not bad. I just got back from visiting my family in Cincinnati, and I kind of missed the snowstorm. So happy to be back in the warmer weather and ability to see sky.
Wonderful. Juan Pablo.
Hi, everyone. Greetings from Phoenix, Arizona. It's 46 degrees right now, so it's a little chilly in the chilly side, but the sky has been clear. I was doing a tour of the planets the other day with a little telescope I got, just seeing Mars and the Moon and Jupiter. But yeah, I'll try to get the occultation of Mars later tonight. Good.
Stephen.
Yes, sir. Good morning from Port Aransas, Texas, which is on a barrier island between Corpus Christi and the next hurricane. And it's 50 degrees with partly cloudy, and we're enjoying probably about the fourth year of a severe drought and are under major watering restrictions. And the sky has been so overcast lately that last night I saw the first stars in about a week. So that's where we are.
Yeah, that's kind of that's what we've had in Tucson all last week. It was cloudy, but only a couple of drops of rain. I think it's been a couple of months since we've had any rain here. Father James. You're muted.
I'm in Southington, Connecticut, and it's
cloudy today, as 40 in the 40s. I've been enjoying views of Jupiter and Venus in the night sky. I think I found a view of the horizon that I can possibly see the comet in the next couple of days. And I've been enjoying the book that you recommended in that ARC podcast on about the We Three Kings of Orient are.
Wonderful. Christopher.
Greetings from New York City, where the weather is very much like it is in southern Connecticut, low 40s, glimpses of blue sky, and I have seen a couple of planets in the sky, so it's always nice to be reminded here in Manhattan that there is actually a sky above me.
Gary.
Hi, I'm here in Milwaukee, Wisconsin. A little chilly out today, about 8 degrees, and I've just been trying to watch the positions of the planets at night.
Timothy.
Good morning. I'm in Westville, Illinois. It's 15 degrees Fahrenheit. And I woke up this morning to a western view of the moon setting. Looked like an awfully full moon. I guess it's going to happen tonight. But it was beautifully yellow. And so I took a picture of it. Doesn't come out when you take a picture, but I took a picture of it anyways. But it was really beautiful.
Justin.
Justin from Watertown, Connecticut. So between James and Christopher, it's 35 degrees here. I've been watching a couple instances of the Northern Lights and looking forward to the planetary alignment on January 25th.
Fabulous. Alfred. You're muted.
Hi, yeah. Works just south of Minneapolis, and it's 3 degrees here. Fahrenheit, not Celsius, 3 degrees zum Teufel. So the nice lake behind me is, of course, a sheet of ice. And I would have changed my background if I could have figured it out how. to show you, there are a few fishing huts, ice fishing huts scattered over it.
Fabulous. Pam.
Morning. I'm in Glendale, Arizona, very close to Juan Pablo and Joe Stickney. It was right a little below freezing this morning. That's why I'm wearing several layers, but it's a beautiful, clear blue sky right now. And I think we're going to have a nice day. And I'm happy to be here.
Carmen, tell us how hot it is where you are.
Oh, well, we are in full summer. Today, 30 centigrades. We are enjoying the beach, but the problem is that it gets cloudy at night. So all the sun and the clear day turns into a sort of darkness, absolute darkness. So no view of anything, and it is very windy, extremely windy, as it has been for years. Thank you.
Larry.
We're hearing things that Zoom decided to not tell me that it was 0% for the sound, even though everything said it was on. But I am in Tucson, north of where Rob is, and it was because we're in a low-lying area. It was 25 this morning, and I think it's mid-30s now, warming up to probably 59 or 60.
And remind me of what time the moon occultation is supposed to start tonight.
There's a occultation of Mars. That's the bright red thing that's low in the sky just after sunset in the east. And the moon will occult it in Arizona about 6:15, West Coast about 6:15, and on the East Coast an hour or two later, depending on where you are in the path.
It should be fun to see. Maureen.
I've got I don't know if anybody else has a site for the location, but I have one if you want me to post it.
Yeah, go ahead, post that, please.
Yeah, put it in the chat. Maureen.
Hi, I'm in Manhattan, and as usual, I don't see much of anything here. I just see Jupiter and Venus a few times. they're pretty hard to miss them even in Manhattan.
Right.
Nothing else new and exciting except that the Eagles won last night, and of course I can't shout and carry on about that in the middle of Manhattan. So I'm sure.
Dave.
It's 41 degrees here in Knoxville. We've had some snow and bad weather over the weekend, but it's clearing up. Last night was very clear. I got my Sea Star, which I got for Christmas, out and took some pictures of the Pleiades. So that was fun.
Excellent. Mark.
I'm in Edinburgh, Scotland. It's about 5 below zero, 5 degrees Celsius below zero. So it's heading towards 10 below zero tonight. So cold, cold, cold. But it makes the stars shine brighter, doesn't it?
Yep. And Rosemary, you're muted.
I had to unmute because my dog was barking. I missed the beginning because I had some trouble logging in, but we've been having pretty clear skies here. Unfortunately, very bitter cold and very high winds.
That's in New Jersey, right?
Yeah, we're in Bayville, New Jersey, down the shore. Tonight supposed to be clear. Right now we're cloud covered, so who knows? But I got addicted. I bought a Dwarf 2 after I saw Father Jim's last year. So I'm having a lot of pleasure putting that little sucker outside and sitting in the warmth of my house looking at different things. So
wonderful. And I'll end up with Bob. Tell us what the weather is in Michigan.
Sorry, eating lunch here. It is bone chilling out there. My computer says 26 degrees Fahrenheit, and my wife just got back from shopping, and the 30 seconds bringing food in was just cold.
That's what it was here in Tucson this morning. Yeah.
Yikes.
Sorry about that. All right. I don't see Paul here, so I'll just give a brief update of what's happening with our telescope. Since the last we spoke, we had an issue on the Vatican Observatory's Advanced Technology Telescope where the derotator stopped derotating. Now, this is something that is kind of odd. A typical amateur telescope or older telescopes would have one axis that where the telescope turns on that axis to follow the stars across the sky. And when you do that, the picture of what you're taking stays steady with the sky. Now, our telescope, built 30 years ago, but still pretty advanced, was an alt-azimuth telescope. So that it goes this way or that way, which means you have to have a computer control to actually follow the stars in the sky. And when you do that, the image of the stars has to be actually rotated. The camera has to be rotated so that the stars stay in the same position. And this is all very easily done when it works. But the gears, after 30 years, had been clogged mostly with dead moth bits. So we had to take the derotator off the back of the telescope, take it into Tucson, make sure that there wasn't anything more serious wrong with it. It wasn't. They did a thorough cleaning in the lab, ending with taking it out to the university's carpool, which is not a pool where you wash cars, but it is a place where you wash cars, and running the derotator through the car wash to get the last of the bits off. Apparently, it's being taken up to the telescope this morning and being reattached, and the telescope should be back in business in the next couple of days. So one of those odd things that happens every now and then. My suggestion is that we should line the entire dome, where, of course, nobody lives because you don't want a human being in with the telescope. Your heat will destroy the telescope image. But I think we should take the walls of the telescope dome and turn them into cedar to keep the moths out. I'm not sure that would work. Or just have mothballs.
It'd be pretty.
I'll end with the one story, about 20 years ago. I was actually at the telescope observing trans-Neptunian objects. And we had turned to one object, which was out about where Uranus was. And instead of seeing a dot, we saw a cloud of light next to the dot. If the cloud of light was immediately around the dot, you'd say, the object is outgassing. Well, this was an outgas, but it was not the exact same object. It was a little bit disturbed to the side, which was very odd. So we took a bunch of images. It turns out we were not the first people to find this. We were the second people to find this. And so they wound up writing up, it looks like this was an object that had broken up in its previous closest pass to the sun. And this was a smaller bit that was outgassing and making its own little mini comet. The difficulty was all the images we had of this very, very rare thing were taken on April Fool's Day, so who's going to believe us? And right across the bottom corner was the leg of a dead moth that had gotten itself wedged into and in front of the CCD chip. So that's the one issue we have. Of course, when we were closed down for COVID, we went back there and discovered that the dome was just full of dead moths. So somehow everybody's worried about, the squirrels dying, and nobody cares about the moths dying. So it goes for the latest news of the telescope. With that, it's my pleasure to welcome with us today Nancy Chabot. And Nancy, I've invited to this because we have many things in common. We're both meteorite scientists. We're both officers of the Meteoritical Society. She is now the past president, and I'm the current president, the new president. We're both PhD graduates of the University of Arizona, and both of us, in fact, worked for a while, in my case, with the same advisor, Mike Drake. Nancy, I was looking up when I arrived at the University of Arizona in May of '75. I was 22 years old. Mike Drake was 28 years old. He was only 6 years older than me.
Is this where I tell you how old I was?
Go right ahead.
I guess I was 3.
Oh dear. I was not expected. I was hoping 12 or something like that. Tell us a little bit about yourself then. Where were you when you were 3? Where did you grow up?
I grew up in the Los Angeles area. So, just sort of out there in what is LA, and we moved around a bit, but always a Southern California girl at heart. I think that's stuck with me. I'm in the Washington, D.C. area now, and we got about like 9 inches of snow here recently, and I still don't like snow. People who think they need seasons, I think it's just overrated. Really, if you just live in a place that has lovely weather all the time, it's amazing. So that's my Southern California experience.
Well, in Southern California, what was your family like? Were you an only child or one of a billion, and what did your folks do?
I have one sister. She's 2 years younger than me, and both my parents actually teach math, and they met at Notre Dame in grad school. So the first song that I learned as a child was the Notre Dame fight song. So Maureen was talking about football wins, so I'm very excited about Notre Dame, and I'm also excited about the Ravens and the Commanders still pulling it off. So we've got a lot to root for on the football front over here in this household. So yeah, so that's why we lived in LA. My dad taught at Cal State LA, so that brought us to that area, and we grew up in that area.
Where did you go to school?
I went to undergrad at Rice University, which is in Houston, Texas, which to a lot of people might seem like a weird choice when you're in LA, and there's a lot of great schools in California. But having been in California my whole life, I was kind of looking to just sort of expand my horizons a little bit. And Rice is a fabulous school. It's small, which really appealed to me at the time, and it's very affordable. They have a very large endowment. So yeah, so it was a great place to go to school.
Did you have the dream even as a kid? You wanted to be an astronomer, or what was your original major?
They get this question. I think really I wanted to be a dolphin trainer for a long time, but that's probably growing up in Southern California. But when I had to pick a major going to college is when I really started to think about it and think about, if you're going to spend that many hours of your life, what do you want to do? Was always good at science and math, probably a prerequisite with 2 parents who teach math, that they were going to make sure that was that case. But I really credit a lot of my desire to go into space science with when I was thinking about this going into college and being inspired by Star Wars. So I think that I'm fundamentally a dreamer. It's I think, and when I thought about it, what I really liked about Star Wars was not just the stories, but all of the unexplored worlds, right? Worlds where people live in the clouds, worlds that are covered by ice, worlds with 2 suns, and just sort of that fundamental seeking out and exploring, you know, beyond our planet really drove me. So I was very into space science and astronomy. And then I went to grad school at Arizona, like you said, and that's where I realized that planetary science was a thing. I always thought just astronomy was telescopes and you have to look at things that are far away. And going into planetary science, I really enjoyed sort of, it's close enough that you can actually potentially get there. You can hold meteorites and pieces of space in your hand and study them. So it's like the accessible space, and those two together just have hooked me ever since.
Were there museums or something as a kid that got you interested in meteorites?
No, I actually knew nothing about meteorites until I went to grad school. I mean, I did space physics at Rice because Rice is a small school and that's sort of what they're known for. So I did magnetospheres and that sort of stuff. I spent 3 summers in Los Alamos, which was fabulous, beautiful place to go to school. And so having lived in Los Angeles area and then going to school in Houston, you know, we had taken vacations to national parks, but I took this tiny little plane when I got the summer internship from Houston to Los Alamos, and we landed, you know, and there's like nothing. And I told my parents, like, I'm doing a summer internship in a national park because, you know, it's just so beautiful and gorgeous there. But yeah, so I did sort of space physics. And when I went to Arizona, even, I wasn't working with Mike Drake on meteorites. Originally, I was doing other things. I worked on helping to calibrate the imager for Mars Pathfinder. I did some observations of water on Mars with Don Hutton. And then it was really the lab work and the accessibility and things just sort of clicked when I started working with Mike on meteorites. So I'm pretty new to the meteorite world, I'd say, even though now it's been decades. So I suppose I can't really call myself new anymore.
Well, when you arrived there, who were you originally working with?
Sort of with Peter Smith, and you know, on sort of the
So that was the
yeah,
Mars Pathfinder. So that would have been in the 1990s.
Yes, yeah,
Right.
94 is when I started there.
How did you connect up with Mike?
Well, you know, again, I was in grad school. I was on fellowship, so I was lucky enough to sort of have some flexibility to explore a lot of different topics. And I told him I wanted to do some stuff in the lab, just because I thought maybe that would be interesting. And it was. I was just sort of, I really liked being able to not just sit behind a computer screen all the time, but actually get into the lab and touch some things and make some things.
What did you do in the lab?
I melted stuff. This is still what I do in my lab, pretty much.
Describe where the lab was and what you did, because I remember that lab. I remember the ovens that he had.
Yeah, so the lab was in the basement, as most labs are. It seems, you know, it's stable for the floor, so they really put a lot of labs in the basements of buildings, and you know, and I guess you don't really need sunlight if you're down there working in the lab, so you just work in the dark all the time. But anyways, yeah, so the lab had some high pressure furnaces, some high temperature furnaces. So you could, that had come out of the Apollo days, actually. So when they first started to bring rocks back from the moon, they wanted to do experiments to try to recreate those rocks. What is the mineralogy? What, when you measure this in the lunar rocks, are you seeing? And what does that mean about the temperature that they experienced? So, but then this also got applied to meteorites through the years. And my focus, and Alfred is on here, was a lot on iron meteorites. And iron meteorites as relate to the central cores of asteroids, where the metal and the rocky parts had separated, and how did that happen, and what does that chemistry mean? And
so you came into this as a plasma physicist, essentially. So you had to learn a whole lot of chemistry real fast, and maybe a whole lot of mineralogy real fast. Is that how that worked?
Yeah, I mean, I had a straight up physics degree. The only geology class I had taken was geology of national parks. So yeah, in grad school, you had to learn a lot of geochemistry. That might be why most of my meteorite research is mostly on iron, nickel, metal. So I'm not even sure how much mineralogy and petrology I know. Sometimes, you know, kind of, if you just melt all the things and make all the minerals go away, then, you know, you just have a liquid that's a little easier. So that was the solution there. But yeah, no, I think that's one of the things that's exciting about planets, is that they are systems. Right? It's not just one discipline. You need to know the physics and the chemistry and the geology and the atmosphere, if it has one, you know, and how these all work together. So it's a very interdisciplinary field, which is exciting because you can't have somebody who actually is an expert in all of those different things. They have to come together to try to understand what we're dealing with.
Well, what was the question that you were working on? Why were you melting these iron meteorites? What in particular were you trying to figure out that people didn't know before?
One of the main things was how different were bodies that formed in the early solar system. So like if an asteroid forms a core and makes it metal and is that the same? Is that absolutely the same wherever it happened in the solar system, or were there differences? And the iron meteorites gave a lot of insight that there are actually differences whether it formed closer to the sun or whether it formed in the outer solar system further from the sun. And the meteorites are sort of these hold the chemical signatures of those differences. But you can't interpret those chemical signatures unless you understand the behavior of those elements. So lots of different metal-loving elements, measuring how they would go into the metal phases, into the liquid metal versus the solid metal versus the rock, and then using that data in order to interpret the different groups to understand any one asteroid, but then really to get at the population, to understand what are the processes across our solar system that led to the bodies that we have today. And of course, these are interesting to look back at 4.5 billion years ago, but they're also the building blocks of our own planet, of the Earth, of Mars, of Venus, of Mercury, right? So, understanding them isn't just to look back in time, but it's also then to understand what were the materials that were making the planet that we live on.
What were some of the wonderful elements that you were actually measuring? We've got a number of people here with a pretty good science background, so don't be afraid to be a little technical.
Platinum, rhenium, osmium, molybdenum, tungsten. My favorite element right now, which you didn't ask me, but I will tell you anyways, is antimony. Antimony has some fabulous partitioning behaviors between solid metal and liquid metal that I will geek out about on there. A lot of the elements that we would look at that have a strong effect is how much sulfur is around, how much phosphorus is around, how much carbon is around. These have a huge influence on how of these trace elements then partition into the different phases.
So as one of the world's leading experts on cores of planets, what's the light element in the Earth's core?
The light element in the Earth's core is probably a mixture. I mean, that's the basic going sort of theory these days. So, a little bit of silicon, a little bit of sulfur, probably a little bit of oxygen. The Earth's core is very interesting at the high pressure, very different than the asteroids. So for the asteroids, it really seems to be dominated by sulfur. We have very few iron meteorites that have any evidence of having silicon in their core, for example. So that's a fundamental difference. I also worked on Messenger, which was the first spacecraft to orbit the planet Mercury. And so this was a nice way to then transition, because of course, one of the things that we know about Mercury is it has a gigantic core, right? Like it's basically a big hunk of metal surrounded by a tiny little bit of rock around it, right? So what's that core? What's the light element in that core? My bet is that it's largely silicon, which is just fascinating to think about, how that evolves, how it makes the magnetic field, how that's different than the Earth's magnetic field and the generation and the dynamo.
How can you tell the difference? How can you tell whether it's silicon versus sulfur?
Well, it's hard, right? I mean, on the Earth, we have a lot of tools at our disposal, which is a fun thing about planetary science and the Earth being a planet, right? So you can do seismology, for example, right? I mean, so we have a ton of information about the Earth's core because we can actually, we are here and we can make measurements constantly. For the other planets, it's much more limited. So the spacecraft, you can get the moment of inertia and then the distribution of the gravity and the planets gives you data that you have to fit, but then you make a model of different layers to try to explain what you're saying. And that gives you some idea of the density of these materials in order to do that. But one of the things, I'm also on the BepiColombo mission, which is ESA's mission that's going to go and orbit Mercury. It just flew by Mercury a few days ago. Maybe some of you saw those spectacular pictures, very successful Mercury flyby I just executed by BepiColombo. They're going to be in a closer orbit than Messenger was. And so they're going to be able to get gravity data that we weren't able to with Messenger. And from that, they might be able to tell where the boundary between the liquid inner core, the solid inner core and the liquid outer core is, which would be very exciting to get that marker, because that's a place where you have active phase chemistry happening. So it should give you one pressure and temperature space, which will be tied to the composition. And so I'm very hopeful that BepiColombo can make that important measurement.
You mentioned spacecraft missions. So, of course, the real question is, how did you wind up in these missions? Tell us what happened when you graduated from University of Arizona. What was your next stop?
So once I graduated from University of Arizona, I went to Johnson Space Center in Houston, Texas, which was great. It was always sort of a dream come true, having worked on this in order to be like going to NASA on a fellowship, and going there was to continue to do the experimental work that I was doing, bringing it to higher pressures, in particular, looking at the moon's core, or looking at the core of Mars and the cores of Mercury's and things like that. So, and so that was a great opportunity, and I really enjoyed it. But then while I was there, about a year into the fellowship, this other opportunity came up, which was they were looking for someone to lead a second field team in Antarctica to search for meteorites. And this was, I had gotten the privilege of going once in grad school to Antarctica to be part of the Antarctic Search for Meteorites program, ANSMET. And it was an amazing opportunity. So here they were looking to expand the search to have 2 field teams and hiring a postdoc in order to lead that second field team, working with Ralph Harvey at Case Western Reserve University. So I applied, got that position. So I left NASA actually from that fellowship and went to Case Western Reserve University and started looking for meteorites, which I know you want to jump in there.
Yeah. Well, how many times? I've been to Antarctica once. How many times have you been?
I've been 5 times. So once I went in grad school, and I have very fond memories, Guy, of you telling me all about your trips and presenting to us and sharing the photos, and just, you know, it's an amazing opportunity. I mean, Antarctica, I can still kind of close my eyes and picture it sometimes, right? Like the big skies that go on forever, the winds, the quiet, the sun. Beautiful, beautiful. But then collecting the meteorites is also just such a scientific treasure trove. I mean, these things are made available to scientists around the world. And so I find it really rewarding to be part of a program like that, where it's so much bigger than just your science. You're like giving science and enabling so much to happen across the whole community. And so that was a lot of the appeal with leaving NASA to take the ANSMET position, was to be part of something bigger. I found that really rewarding, and I had realized once I was doing the lab work that I enjoyed that, but I felt a little isolated, and so being part of a bigger team was something that I realized was important to me. And yeah, so I've been 5 times, and then I went 4 times while I was at Case, doing the second field team activity, where I would be the science lead for that field team.
Now, everybody who's been to Antarctica has full of stories. Tell us one story that you are not afraid to tell in public of something wild and crazy that happened while you were in Antarctica.
Oh, gosh. I don't know, one wild and crazy story of some time in Antarctica. So I think one of the best ones that relates to meteorites actually is we were driving around in this new ice field. We were on a pretty small field team. There were 4 of us total, because they were doing what we were calling recce, or recon work. So we had gone to a blue ice field where basically probably people had never been, honestly. Maybe we might have been the first humans to be walking around some part of this continent. And so you're on your snowmobiles, and the way it works is you kind of drive pretty far apart from each other, and you know, try to see if you can find any rocks from space. So we're doing this, and anybody who's seen this, you know, most meteorites that you find you're lucky if it's the size of a golf ball. A lot of times it's maybe half a golf ball or a quarter golf ball, you know, so you're talking pretty small. They can be even smaller than that. But you still get excited. Analytical equipment can look at things and get down to the atomic level, right? So these are still very valuable samples. Well, we came across this palisite, which is a mix of metal and olivine. And it was like, you know, like the size of a bowling ball. Right. And this and so we're like, oh my gosh. And so everybody comes over. So when you find a meteorite, the first thing you do is you like flag everybody else down by going like, hey, I found a meteorite. And then everybody drives their snowmobiles over, and you get there, and we're just like oohing and eyeing over this giant palisite that we found. I mean, it probably weighed like 70 or 80 pounds. I could barely pick it up. Okay, so then that's great. We collect it, we get back on our snowmobiles and continue. And then somebody found a second one. And then we found a third one, and we found a fourth one. And I mean, overall, between like the 2 or 3 days that we were there, we wound up finding, you know, 10 or 11 of these giant palisites, and it was just amazing. I mean, and there were ones that I couldn't pick up because they were so massive.
They from the same fall, you know?
Yeah, Yeah, so I mean, when they got them back there to the lab and people have studied them, you know, they are from the same fall. So it's a strewn field that's out there that's in Antarctica, you know, which maybe scientifically makes them less exciting that they're all pieces of the same thing. But in some ways, I mean, it doesn't change the excitement of finding them. Trust me, they're like, it was amazing. And it also is a really cool opportunity because, like I said, a lot of meteorites that we find are small and they don't have, you know, you're kind of like, what does it look like on the bigger scale? And with this palisite strewn field, you can study that in a way that is not possible for most samples. So, so yeah, I kind of remember that. I use that picture a lot still, actually, with me next to one of the giant palisites when I give talks.
All right, so you were at Case Western and you were there for a few years. What happened next?
So after doing the Inner Search for Meteorites for 4 seasons, I decided to agree with my parents that I should get a quote unquote real job and you know, maybe settle down a little bit. It is great going to Antarctica every year, but my position at Case Western Reserve was not permanent. It was a postdoc position. And also, you're gone a lot, right? I mean, so basically you leave sort of mid-November and you come back, you know, the end of January, or maybe you take a little vacation and it's the middle of February, which is fine when you're living in Cleveland, Ohio, because that is a great time to get out of Cleveland, Ohio. So there was nothing wrong with that. But yeah, I think I just kind of got to a point in my life where it's like, all right, I want some stability. I want to live someplace where I can paint the walls of my room. That became a big thing for me, where you just, you know, something that's yours, that you can settle down, that you can kind of, you know, put down roots a little bit. And so that's where I got personally. And yeah, so I put out job ads for lots of places and never heard back from most of them. And then Johns Hopkins Applied Physics Lab had me over for an interview, and I went and interviewed and got a position there. And that's where I've been now, coming up on 20 years.
So that's how you got involved in spacecraft missions.
It really is. I mean, I've just been fortunate in this position. I don't think that would have happened because, as I was explaining with the background, I have a physics degree, and then I went into meteorites and doing experimental geochemistry. And the space missions is really just being in the right place at the right time. And so Messenger had just recently launched when I started at APL. And, you know, there was a lot of activity that was picking up consequently. And my start actually on the Messenger mission, which was the first spacecraft mission that I worked on, was updating the website. I was just willing and happy to contribute in any way that I could. And the website said this sad thing, like, will be updated after launch. And it had been launched already. And I pointed this out. I was like, hey, maybe we should update this. They're like, oh, that sounds like a good thing that you can do. And I said, okay, I will. And then, you know, they're like, oh, you know so much about the mission. You should start coming to this thing. You should start getting involved with this activity. And so I started doing the featured web images, you know, as part of the website, like, put an image out there. This is amazing. We're flying past Mercury for, you know, this first time that we've seen this planet in many years. Yeah. Yeah. Well, I mean, the first time that we've seen parts of the planet, right? So, you know, 45% of it had been seen previously, but was the first time that we were seeing some parts of the surface.
No, if I remember right, Sean Solomon was the PI of that mission, right?
That's correct. Yep. Down at Carnegie in DC.
Right. When he was at MIT, he was my postdoc director. So there's another overlap between your work and my work.
Yeah.
My goodness.
Yeah. There you go. It's the community does kind of weave together, right? Which is a fun thing too.
Well, it sounds like you were doing lots of outreach kind of work on. Did you eventually get to use some of your science for the Messenger mission?
Right. So doing the outreach for the web images led to the camera team asking like, hey, would you like to work on analyzing the data since you're already like dealing with the images? And so I joined the camera team, and then eventually people who were leading the instruments got into more leadership positions. And so by the time we got into orbit around Mercury, I was actually the instrument scientist for the imager. So I was in charge of the imager for mapping out the planet Mercury for the first time with a team of people. And so to go back, this is one of the things that I really like about being at APL and being on the space missions. It really resonates with me to be part of this team where you do your part, but then it's so much bigger than any one person could accomplish on their own. And so being in charge of the camera was the same sort of way. Like there was a team of people and we all worked together in order to develop the operating strategy, to take the images that are needed, to make the global mosaics. The first time that we had ever completely seen the planet Mercury, you know, and every time I see those globes out there, anytime that people use Mercury for anything and they use some of our images, it just makes me so happy that we've changed the way that people see this planet in their mind and use it going forward. My personal research on Mercury then deals with the ice deposits at the poles. So the permanently shadowed regions, they're the North and the South Pole that never get direct sunlight and have evidence of water ice there. So I've written a number of scientific papers about those.
So from that, what other missions have you been involved with?
Well, the next major mission that I got a chance to be a part of was DART. So as you, you know, see behind me and behind Bob over there, we're rocking
Explain
our
to everybody what
Dimorphos
DART
images.
is.
DART
Yeah,
is
explain
the
what DART
Double
is.
Asteroid Redirection Test Mission, where in September of 2022, humanity deflected an asteroid for the first time. So we purposely crashed a spacecraft into an asteroid and changed that asteroid's position. So this was a technology demonstration mission done for planetary defense. So this is the sort of thing that maybe you would do if you found an asteroid and it was on a collision course with the Earth and you wanted to prevent that impact from happening. So the asteroid that DART crashed into, the DART spacecraft, was not on a collision course with the Earth. The T in DART stands for test. This was definitely just a test. And in fact, it was only the moon of a binary asteroid system. So Dimorphos orbits around Didymos. And so we changed the path of Dimorphos, the moon, around Didymos ever so slightly. It's actually only a few % change. But this is what you would want to do if you were going to deflect an asteroid versus disrupt it. Disrupt it, make it into a bunch of pieces. You don't want to do that because then you have a bunch of pieces. You're not really sure what's going to happen. So the whole idea of planetary defense and a kinetic impactor like DART would be to change the asteroid's position slightly, but do it many years in advance, 5, 10, 15, 20 years in advance. So that small change adds up to a bigger change in its position with time, and the collision course with the Earth is avoided, and the Earth and the asteroid can just go about their merry way going forward. So it was a very exciting mission.
I remember somebody explaining to me, if you had an asteroid with a 50% chance of hitting Earth and you blow it up, you then turn it into a bunch of asteroids with 100% chance that half of them will hit the Earth. And that's not an improvement.
Yeah, it depends on the size. We actually have this debate in the planetary defense community. Right now, 50 meters is the protocol for the smallest asteroid that you would want to ensure that you would take space-based action. So, you know, disrupting a 50-meter asteroid might be the right call because you would make everything smaller than 50 meters. But in general, it's a very non-deterministic process where a lot of stuff is still headed towards the Earth. If you make it small enough that most of it burns up, that might be a net gain. But for many scenarios, it would not be a net gain, to your point.
Well, what did DART actually find out? What do we know now that we didn't know before?
The reason we had to do this was because asteroids are complicated. You know, this is just physics, right? We know if we crash one thing into another one that, you know, the laws of physics will be that we've pushed it, we've transferred momentum. But we've seen this time and time again when spacecraft have explored asteroids, that they're not just one big hunk of rock. And in fact, what we found with Dimorphos is that it's a rubble pile. It's this jumble of rocks all just kind of loosely held together. So how would an actual asteroid react to a spacecraft being crashed into it? And this isn't something that, you know, you can simulate in the lab or that you can do your models for. Those had already been done. But how would an actual asteroid react? And prior to DART, people had done those models and there were a lot of predictions. People thought that this would deflect the asteroid, but how well would it deflect it? And what we found out is that actually the asteroid helps you quite a bit. So because it makes this ejecta, and the ejecta shoots out in the opposite direction, and it can enhance how much you're deflecting because of this recoil effect. The recoil from the ejecta makes you deflect the asteroid even more. And what we found is that the amount of ejecta was more significant in deflecting the asteroid than just the momentum brought in by the spacecraft. So the momentum that you got by the recoil effect actually made the deflection even that much more successful. So I think one of the main things that we've learned from DART is that this simple approach, just this straight momentum enhancement, there was no explosives on DART. It was just crash a spacecraft into an object at high speed. the asteroid's kind of helping you because a lot of them are pretty weak and pretty loose objects. You get a lot of ejecta, you get this recoil effect. And this means that you might not need as much time, or you could deflect a larger object than you might have otherwise just thought might be possible.
Fabulous. Are you involved in any other spacecraft missions coming up now?
I'm involved in BepiColombo, which is going to orbit Mercury. I'm an interdisciplinary scientist on that team. I'm on the Hera team, which is going to launched in October of 2024 and is on its way to rendezvous with Didymos and Dimorphos. So the same asteroids that DART crashed into, but it'll orbit them and it'll see the aftermath of DART's collision. Interesting what Dimorphos will look like. We named some of the boulders near the impact site, and nobody thinks those boulders are there. They definitely have been ejected. Some people think the entire shape of Dimorphos has changed. In fact, we have good evidence for this, actually, that we've changed one of the axes by about 20%. So the shape of Dimorphos might be slightly different. And so Hera is going to be in a position to do this and get the mass. And then I'm also in the Martian Moon Explorations mission, which is a JAXA mission, which is going to Phobos and Deimos.
Remind people what JAXA is.
JAXA is the Japanese space agency. So ESA is the European Space Agency, which is running the BepiColombo mission. But the Japanese Space Agency is launching in 2026 a mission to the Martian moons, Phobos and Deimos. It'll spend 3 years in the Martian system. It'll get samples of Phobos, and then it'll bring the samples of Phobos to Earth in 2031. NASA has an instrument on this mission, which is called MEGANE, which is a gamma ray and neutron spectrometer. And I'm the deputy PI for that instrument. So this is an instrument that'll get the chemical composition of Phobos, which is really important for figuring out the origin of this moon. This is one of the things I love about planetary science is you can ask these super basic questions. How did Phobos form? Like, why is it there? Earth has a moon, but Venus doesn't have any moons. Mercury doesn't have any moons. And the moons of Mars do not look like the Earth's moon at all. They look like these irregularly shaped asteroid kind of objects. But they're in these orbits that are not like captured asteroids. Instead, they're in these very equatorial round kind of orbits, which means that maybe they formed from a collision on Mars actually, and then reaccreted material. And that's why their orbits are so nice. But they look like asteroids, spectrally and lumpy and irregular shaped. So there's two camps here: captured asteroids, pieces of Mars that came off in a giant impact. And so measuring the composition, you can distinguish between these two, and that's what our instrument is going to do.
Fantastic. Meanwhile, you've stayed interested in meteorites. Tell us how you wound up being president of the Meteoritical Society.
Meteorites is kind of my home. I feel like it's and Antarctica, the Antarctic experience I had as a grad student, I think only solidified that. But the Meteoritical Society meetings are really kind of special meetings. There's usually somewhere between 300 and 500 people there. So you really get to know the community. And it's a very international community from around the world. And so tied together by, this joy of studying rocks from space and associated fields. And so it really does kind of feel like your scientific home. And then after you've been to Antarctica, even once, you've had a very close experience with a number of other people where you've been the only other humans around in the field for 6 weeks at a time, living in tents, right? And so you have that. But I did that 5 times, right? So there's so many people in this field that I have these very unique experiences with. So even once I went to APL, I started a meteorite lab. I have my own 2 furnaces where I continue to melt things to this day. I have a lot of summer interns each summer that I bring in to do that. And I've had some NASA grants in order to keep the iron meteorite melting kind of work going and just keeping an active presence in that, even with the spacecraft missions ramping up or being busy. So it's kind of been my grounding in my home. And so when I got the opportunity and the invitation to become president of the Meteoritical Society, I was just overjoyed. I remember my first Meteoritical Society meeting in 1996 in Berlin, and thinking like, I want to be president someday, when Hat McSween was doing the invitation. And so I was really happy to do that for the last 2 years and happy to be working with you, Guy, for the next 2 years as you take over.
I'm very happy you're around because you did a fabulous job. You're very hard to act to follow, and I'm going to continue to lean on you for advice of what am I supposed to do now?
Well, I think the thing that makes the Meteoritical Society, so great, again, it's like one of these team things, right? So much bigger than any one person can do on their own. And just the diversity and the different perspectives that everybody brings to the society, but still unified by that common goal. It's really a beautiful society.
There's, maybe 100 members of that society, 1,000 members of the society, and more than 100 are on various committees doing various tasks. It's not the society and then a small group of people doing all the work. It's stuff that we share. And
it is.
I mentioned when I joined the Vatican Observatory 30 years ago, I no longer had to worry about grants, and I was given the freedom to do whatever science I wanted to do. And after trying out various projects that I had had in the back of my mind, I really wound up centering on meteorites in no small part because I liked going to the meetings. I liked the people I ran into. These were the people where I wanted to say, hey, look at the cool thing I did this last year. And that makes being a scientist so much fun. And I hate to say it, there are corners of our field that are not like that. So life is too short.
Well, I brought my sister to the Meteoritical Society meeting this last year in Brussels, right? And so my sister teaches physics at RIT, the Rochester Institute of Technology, because, we had math professors for parents. So this is what one does, I suppose. She was like, this is not like the physics conferences when she came to the Meteoritical Society meeting. And I'm like, you're right, it's not, because it's like a family, it's a society, right? It's not just it's about the science and it's about sharing the results, but it's more than that.
Well, let me then end with a more philosophical question. At the end of the day, why are you doing what you're doing? Why are you doing this? What gets you up to go into the lab in the morning and keep doing the same old stuff?
Definitely what I find most rewarding about this is that we're advancing what we know, like advancing humanity's knowledge. And in a way, for me, that's rewarding is by a bunch of people coming together to accomplish something that's so much bigger than any one person could do on their own. I know I say that over and over and over again, but for me, that's like fundamentally it, being a part of something where we're working towards a common goal. And when we get to that common goal, we have that common appreciation, and we've increased what we know about the world. So it's that's why I enjoy sharing what I get to do so much. It really is a privilege to be able to doing with this and to work with other people to make it happen. That's why even once I retire, I'll probably be, looking up at the night sky or keeping up with what's going on with space missions or showing up to Meteoritical Society meetings, right? Because just so fortunate to have a career, which is also such a passion.
Thank you very much. Now I'll throw it open to the group here. If you've got questions or comments, feel free to raise your hand or type them into the chat. Anybody who wants to ask Nancy about, the work she's doing or what she hopes to do, if she wants to go to space herself, any of those sorts of questions. I'd like to know what you'd like to know. So, okay, here's a question. What's the role that the U.S. Space Force is going to play in planetary defense? Or is that a NASA responsibility? Whose job is that?
So in the United States, it is a civil endeavor currently. So that means that NASA is the lead agency for that. That said, it's not just NASA. So there is actually documents from the Office of the President that have a national strategic plan, and it's multiple agencies, one of which includes Space Force and also other ones like FEMA, for example. We've done tabletop exercises at APL, which, because it would be a disaster preparedness sort of activity. But right now it is NASA-led, civil-led, and that's the strategy that the country has laid out to continue to that go forward. There's a lot of aspects for planetary defense. Crashing into an asteroid is one tiny part. Finding where the asteroids are in the first place is the foundation, because you can't do anything about them if you don't know where they are. NEO-Surveyor is NASA's next mission in order to put a dedicated telescope into space to find the asteroids. One of the things that's fascinating about planetary defense, too, is it's really growing. so much in the last decade. So NASA stood up the Planetary Defense Coordination Office in 2016. ESA recently, the European Space Agency really stood up their Space Security Office, which deals with planetary defense. Against on the civil side, Japan recently stood up a planetary defense office just within the last year. And so people really are trying to work internationally on this issue of planetary defense. There's 2 UN-endorsed committees, actually, that deal with this, the IWAN, International Asteroid Warning Network, and Same Page, the Space Mission Planning Advisory Group. And so I think there is a lot of push here to make this an international effort. We're all on this planet together to work via the UN on Same Page. For example, China is a member, as is Russia, as is the United States, as is, you know, Europe, and a lot there. So so I think for right now, there's a lot of push and momentum in order to keep this a civil endeavor, and Space Force has resources that they can contribute. If there was a threat discovered that was actually coming towards the Earth, that would be very different. We're trying to be in a position where we would have long warning times, so you don't have to take drastic action at the last minute. But if you do have to take drastic action to protect the planet, then obviously it's a very different conversation.
How many asteroids are still left to be discovered at this point?
A lot. So this is the thing. So kilometer-sized asteroids are sort of the cutoff on where people think you might get climate changes, aka it might be a global disaster that would happen. The good news is that for a kilometer and larger near-Earth asteroids, we found about 95% of those, and none are a threat to hit the Earth for the next 100+ years. But then people talk about 140-meter asteroids, which is this cutoff size for sort of regional destruction. These could still have tens to hundreds of kilometers of devastation if they were to hit the planet. And you could wipe out a city, a small state, a small country, potentially, if you were over a heavily populated area. And of that size, the 140 meters, we found less than half of that population currently. So of the half that's been found, none are a threat to hit the Earth for the next 100+ years, but that still leaves tens of thousands of objects yet to be found of that size.
Rob, you have a question.
Yeah, so have we ruled out like Apophis being a threat? Is that
Apophis will not hit the Earth. Apophis will not hit the Earth. Apophis will not hit the Earth. This is this is what they say over and over, that you have to say it 3 times, and it's very important. Yeah, no, Apophis will not hit the Earth. Now, Apophis for everybody is 2029. If you just for a while, if you just typed in 2029 in your browser, Apophis would come up. It was like the #1 thing. It's about a 340-meter asteroid that's going to pass very close to Earth. In fact, closer than some geostationary satellites, right on the edge of there. It's going to be visible naked eye in Europe and parts of Africa if the weather cooperates. And so this is a very time for awareness for planetary defense. NASA has a mission that's called APEX, the Apophis Explorer, which is the old OSIRIS-REx spacecraft that's actually going to orbit Apophis after its closest approach with there to really characterize it. Europe is working on a mission concept called Ramses, which would get to Apophis prior to its closest encounter, so to see it prior and after, because the tidal forces might change the asteroid slightly. Other people are looking at a number of missions, small sats, CubeSats, in order to characterize the asteroid. So Apophis is a great opportunity for characterization. And the United Nations just recently, within the last few weeks, made 2029 the International Year of Asteroid Awareness. So I think you're going to see a lot about Apophis. If you didn't already know about Apophis, you will learn a lot more about Apophis in the coming years. But it will not hit the Earth. It will not hit the Earth. It will not hit the Earth. Okay.
And the last question, what about mining these asteroids? Are you involved in any of that?
So for a while, actually, I was on the science board for Planetary Resources, which was an asteroid mining company. And Luxembourg actually was putting a lot of resources and support into looking at asteroid mining. So asteroid mining is a possibility. Most people would be looking not at metals first, but more at a water to get the hydrogen to make resources in space. Fuel in space in particular is what most people's business models were when they were looking at the asteroid mining. The whole thing seems to, have collapsed, but in some ways, in situ resource utilization, be it on the moon or on asteroids, not having to just launch everything up off the Earth if you are going to have a human presence in space makes sense. So some of it is just if there are going to be humans living off planet, then you're going to want to use the resources that are out there. And so asteroid mining, I think, is one of these things that will come back around. A lot of asteroids are on favorable orbits where they are pretty accessible every once in a while, every 2 years or so, or even shorter, and so you can potentially get to them in favorable sorts of ways. So I do kind of expect that it'll come back around, but it seems like right now there's not a ton of activities going on in that area.
Well, thank you once again for being part of this. And thanks everybody for your great questions. It's now 11 o'clock here in Tucson, and I promised people we'd be finished in an hour. We finished exactly on time. Thank you, Nancy. Thank you, everybody. And see you next full moon.
Thank you for having me. I really appreciate it.
Bye, everyone.
All right.